Hello everyone. In today's lecture we will move on to a new chapter, which is a digital filter design. In the previous chapter we have been talking about the Z-transform, and we have seen that it's a very useful mathematical tool in dealing with discrete time signals and discrete time systems. In the new chapter, in the digital filter design, before we start, I need to remind you with few facts about LTI systems and how we can use the Z-transform in dealing with such systems. So, if you remember, if we have an LTI system whose impulse response is h of n and the input signal is x of n and the output signal is y of n. Y of n can be computed using the convolution between x of n, the input signal, and the impulse response h of n. If we apply the Z-transform to this equation, we will get y of z equals to x of z times h of z, where h of z is a system transfer function. It is a z transform of the impulse response, summation from n in negative infinity to positive infinity of h of n z to the negative n, and y of z is a z transform of the output signal, x of z is z transform of the input signal. And if you remember, z is a complex variable and z is simply equal to a magnitude r and an angle omega e to the power j omega. And if we let magnitude z, which is equal to r, to be 1, this simply means that in the z domain we are moving along the unit circle. In this case, z becomes e to the power j omega, and h of z becomes h of e to the power j omega, and this is known as the frequency response of the system. So the frequency response of a system is h of e to the power j omega. And in this chapter, when we are talking about the frequency response of a system, we are referring to this h of e to the power j omega, which is simply h of z evaluated at the unit circle. Moving on, the previous equation we have seen is simply saying that y of z, the output, is equal to x of z, the input, in the z domain times h of z. If we set r equals to 1 in this equation, we will get y of e to the power j omega equal to x of e to the power j omega times h of e to the power j omega, where y of e to the power j omega is the frequency content, or the Fourier transform, or the spectrum of y of n, the output signal, and x of e to the power j omega is the Fourier transform, or the frequency content, or the spectrum of the input signal, and h of e to the power j omega is the frequency response of the system. So let me write down this terminology. So x of n is the input signal in time domain, and if we use Fourier transform, we get x of e to the power j omega, which is the spectrum of x of n, the frequency content of x of n, or the Fourier transform of x of n. Same for y of n. Y of n is the output signal in time domain. Using Fourier transform, you get y of e to the power j omega, which is the spectrum of y of n. And of course, as you know, the impulse response h of n, when you apply Fourier transform, you will get h of e to the power j omega, which is the frequency response of the system. Now, the previous equation is simply saying that the spectrum of the output signal is equal to the spectrum of the input signal multiplied by the frequency response of the system. And in order to understand this equation, let's move on and draw this spectrum. Let's assume that this is a frequency response of a system we have. And let's assume that this is the spectrum of the input signal x of e to the power j omega. Let's assume it goes like this. So what would be the spectrum of the output signal y of e to the power j omega? Based on the previous equation, the spectrum of the output signal would be the spectrum of the input signal multiplied by the frequency response. So going back here, we can see that the spectrum of the output signal in this region up to this frequency will be multiplication of the frequency response. Let's assume it has a value of 1 by x of e to the power j omega. So this part of the spectrum is actually allowed to pass to the output, whereas this part of the spectrum of the input signal will be multiplied by a 0. Therefore, it will not be allowed to pass to the output signal. So a filter is simply an LTI system whose frequency response shapes or controls what frequency is allowed in the output and what kind of frequency is not allowed in the output. These frequencies were allowed to pass from the input to the output because the filter has a gain of 1 in this case, in this range. And this part of the input spectrum was not allowed to pass because it was multiplied by a 0. So, going back to our slide over here, a filter is an LTI system which is designed to allow a certain set of frequencies to pass, designed to pass a set of desired frequency components from a mixture of desired and undesired components. So here, if this is the spectrum of the input signal, you want to allow this part of the spectrum to pass and you want to stop this part of the spectrum. So you design a filter that would allow some desired frequencies to pass and kill the other frequencies. In other words, to shape the spectrum of the input signal according to the frequency response of the filter. In other words, you are shaping the spectrum of the input signal based on the frequency response of the filter, resulting in this kind of output. The filter design problem is simply trying to find a practically realizable filter whose frequency response best approximates a desired ideal magnitude and phase response. As we are going to see in a few minutes, usually we start with an ideal magnitude and phase response, ideal response. But this ideal response is usually non-realizable, not realizable. So we need to find a practically realizable filter that approximates this desired response. Digital filters are discrete time systems, so they can be classified as FIR filters, finite impulse response filters, and IIR filters, infinite impulse response filters. Remember, an IIR LTI system is represented using the following LCCDE, where the present value of the output is a summation of or depends on the previous values of the output and the present and previous values of the input. And if you remember in the previous lecture, we have applied Z transform to this equation, and we found that h of z, the system transfer function in this case, will be a rational function, ratio between two polynomials. The polynomial in the numerator is depending on the coefficients bk, and if you remember, bk were called the feed-forward coefficients, whereas the polynomial in the denominator depends on the ak, the feedback coefficients. And moving on, this is a signal flow graph of an IIR system. So if we have an x of n over here multiplied by b0 and then unit delay, you get xn minus 1 multiplied by b1, another unit delay xn minus 2 multiplied by b2. So the signal s of n over here is b0 xn plus b1 xn minus 1 plus b2 xn minus 2, which is basically this term b0 xn b1 xn minus 1 b2 xn minus 2. And then you move on and you get a signal yn, apply a unit delay, you get yn minus 1, another delay yn minus 2 multiplied by the coefficients a1 and a2, and then you add them. This is the feedback part of the system. So this is the feed-forward part of the system, and this is the feedback part of the system. Both of them combined are implementing this equation, which is an IIR LTI system. For an FIR system, on the other hand, the feedback coefficients are equal to 0. There is no feedback, only feed-forward part. So the equation here, if you set AK equals to 0, you will get yn equals summation bk xn minus k. So it's basically yn equals to summation bk xn minus k. And if you remember, we had a discussion about FIR filters in the introduction chapter, and we have seen that the impulse response of FIR filters are simply the coefficients bk, and we have proved it in detail that bk is equal to h of k, the impulse response. So applying that transform, we will get h of z, which is y of z over x of z. In this case, if you go back over here and set ak equals to 0, h of z will be simply this summation from k to 0 up to m bk z to the power minus k, which is summation of h of k z to the power minus k. This is a block diagram of an FIR filter, and as you can see, it's basically delays z minus 1, z minus 1, z minus 1, and then you multiply by the coefficients h0, h1, h2, and you add them together to get y of n. As you can see here, there is no feedback, it's only a feed-forward system. And as we have said before, for an FIR system, the filter coefficients bk are equal to the impulse response hk. So the algorithms used to design FIR filters are different from those used to design an IIR filter. So basically, to design an FIR filter, we usually perform it either in time domain using what's called the windowing method, or we can do it in frequency domain using the frequency sampling method, or the optimum Chebyshev approximation using the Parks-McLennan algorithm. On the other hand, the design of IIR filters is usually done by converting analog filters into equivalent digital filters. So in IIR filter, in infinite impulse response digital filters, we usually start by designing analog filters, and then we convert this analog filter into digital filter. And towards this end, we use one of two transformations, either the impulse invariance transformation or the bilinear transformation. These two transformations transform analog filters into digital filters, transforms h of s from the Laplace domain into h of z in the z domain. So in designing frequency selective filters, we need to go through some steps. First step is a specification. We need to understand what kind of specifications this filter has to satisfy. And by specification, we mean is it a low pass filter, a high pass filter, a band pass filter, a band stop filter, what are the cutoff frequencies, and other specifications we're going to see later on. And our task or our goal is to translate these specifications into hardware or software that perform or have the frequency response required. The second step is approximation, which is basically approximate the desired frequency response with a polynomial or a rational function. Again, we will have an ideal desired frequency response, HD of e to the power j omega, desired frequency response, but we will not be able to achieve this desired frequency response exactly. But we will try to approximate this desired frequency response with another system that has a frequency response that is a polynomial or a rational function. If it's a polynomial, it's an FIR filter. Why? If you go back over here, if the frequency response takes this form, only a polynomial, so it's an FIR filter. But if h of z takes the form of a rational function, it's an IIR filter. Okay, so the first step is the specification, second step is the approximation. In approximation, we need to meet the specification with minimum complexity. And by minimum complexity, we mean a system that has a minimum order, minimum number of pools, minimum number of coefficients, minimum number of multiplications, and so on. So going back over here, a minimum order means, or a minimum complexity means minimum number of multiplication, minimum number of addition, minimum number of delays. Same for an IIR filter. The third step would be quantization, which is basically the filter coefficients we achieve need to be quantized, because in actual hardware we have finite word lengths. We represent numbers and filter coefficients using finite word lengths, 10 bits, 8 bits, 20 bits. This is called quantization, and the effect of quantization is studied in details in chapter 15 in the textbook. Unfortunately, we will not be having enough time to talk about it. The fourth step is the verification. Once we have designed our filter, we need to verify that the designed approximate filter is achieves acceptable frequency response compared to the ideal characteristics that we are looking for. And we do so through simulation. So we can use MATLAB to simulate the designed filter and make sure it actually approximates the desired frequency response. If not, we will go back to step 2 and try to reiterate the design process. And the last step is the implementation. We can implement the digital filter either in hardware using FPGA or so, or in software. In this chapter, we will consider only the tasks involved in steps 1 and 2, namely the specification and the approximation. So in filter specification, we need to learn what kind of a specification of the filter can have, and then we can how to translate this specification into filter design. So design of frequency selective filters usually start with a specification of the frequency response function. Okay, so the standard types of ideal frequency selective filters either pass or eliminate a region of the input spectrum perfectly. So an ideal frequency selective filter, we have 4 types of ideal filters. So if you go to our whiteboard over here, we have 4 basic types of ideal filter. This kind of filter is called an ideal low-pass filter because it allows low frequencies to pass from 0 up to omega c and kills the higher frequencies. The filter can also be a high-pass filter, like this. This is a high-pass filter, where it allows higher frequencies larger than omega c to pass and kills lower frequencies. We also might have what's called a band-pass filter. A band-pass filter would allow, this is a band-pass filter, a band-pass filter would allow frequencies from omega c1 up to omega c2 to pass and kills all other frequencies. And the fourth type is called a band-stop filter, which is basically something like this. It kills a certain band and allows all other frequencies to pass. This is called a band-stop filter. These are the 4 basic types of ideal filters. So if we consider only the low-pass filter for a second, so an ideal low-pass filter would allow a certain band of frequencies to pass and would stop another band of frequency. So going back to our slides, so a standard type of ideal frequency selective filter either pass or eliminate a region of input spectrum perfectly. So going back to here, perfectly means that the pass band, the region of frequency which is allowed to pass, we will multiply it by 1, so it will pass as is, and the range of frequencies supposed to be stopped or killed will be multiplied by a 0, so it will not be allowed to pass at all. That's why we say over here it's an ideal frequency selective filter, pass or eliminate a region of input spectrum perfectly. And they have abrupt or instantaneous change or transition between pass band and stop band. As you can see over here, we have a sudden change from pass band to stop band. So this range of frequencies is called the pass band, and this range of frequencies is called the stop band. And an ideal filter would have a gain of 1 in the pass band, so all the frequency in the pass band would pass unchanged, and a gain of 0 in the stop band where all frequencies over here will be killed, multiplied by exact 0, and we have a sudden change from the pass band to stop band. This is an ideal low pass filter. Okay, however, ideal filters cannot be implemented in practice. We cannot actually implement such an ideal filter with sudden change and flat pass band, flat stop band. We cannot implement this in practice. That's why we need to approximate such an ideal desired response with a practically realizable filter. We need to look for practically realizable system in order to implement or approximate this ideal desired response. So practical filters differ from ideal filters in several aspects. First one is that the pass band response of an ideal filter is completely flat, whereas the pass band response of a practical filter are not perfectly flat. This simply means that in an ideal filter we have a flat response in the pass band. All frequencies are having the same gain of 1. But in practical filters we might have a fluctuation in the gain like this. So instead of having a flat gain during the pass band response is not perfectly flat. The other difference is that for ideal filter, the stop band gain is 0 for all frequencies, so all the frequencies in the stop band are completely eliminated. Whereas for practical filters, the stop band response cannot completely reject or eliminate bands of frequencies. This basically means that instead of having a gain of 0 in the stop band, we might have very low non-zero gain that oscillates like this. And the third difference is that the transition between pass band and stop band takes place over a finite transition band. Instead of having a sudden change from pass band to stop band, practically we'll have this transition band, a finite band in which the gain drops from 1 to 0. This is called a transition band. This band over here is known as a transition band. Okay. So this is basically what we're talking about over here. The black curve represents the ideal low pass filter with cutoff frequency omega c, and the blue curve represents the actual filter in which we have fluctuation or ripple in the pass band, and we have also fluctuation or ripple in the stop band, and we have a band in which the gain drops gradually instead of suddenly. It drops gradually from pass band to stop band. This is known as a transition band. So if the gain, the ideal gain is 1, we would allow a fluctuation in the pass band by delta p. So the maximum gain over here should be 1 plus delta p, and the gain below here is 1 minus delta p, and the gain in the stop band we will call it delta s. That's why if you go back to the slide over here, we'll have the maximum allowed gain in the pass band is 1 plus delta p, and the minimum is 1 minus delta p, and the maximum gain in the stop band is delta s. Ideally, delta p should be 0, so these two will be basically 1, and it will be a flat response. And delta s should be exactly 0, such that the gain here will be exactly 0. But practically, we cannot achieve this. We can only have a finite allowance for fluctuation in the pass band and in the stop band. And we'll come back later to these two axes over here. So the specification of a practical filter usually takes the form of a tolerance diagram as shown in the previous figure. By tolerance diagram, we mean that any response within this band is acceptable. So if you have a filter response that has a smaller fluctuation, it's acceptable. As long as you're within this band, you're fine. As long as you're within this band, you're fine. So omega p is the edge of the pass band. So here we can see we have 3 frequencies. Omega c is the cutoff frequency. Omega p is the edge of the pass band. Omega s is the edge of the stop band. So omega p, pass band edge, omega s, stop band edge. And as you can see in this figure, we are only talking about the magnitude of the frequency response. The phase response actually is either left unspecified or it may be required to be linear, and in the next lecture we will talk about the importance of linear phase. Since we focus on filters with real impulse response, that is h of n is always real valued, we need to prescribe the specification only in the interval from 0 to pi. This is simply true because if h of n is real valued, h of e to the power j omega will have this property. So if h of n is real valued, then the frequency response h of e to the power j omega will be equal to h conjugate of e to the negative j omega, which simply means that magnitude h of e to the power j omega is equal to magnitude e h of e to the negative j omega. That is, the magnitude response is even function. That's why we do not need to specify the magnitude response for negative frequencies, only for positive frequencies going from 0 to pi. And we note that practical filters may have pass band and stop band ripples as they exhibit gradual transition band. So basically a practical filter is this kind of filter where you have ripples in the pass band, ripples in the stop band, and we have a gradual transition band. And again, the frequency response, the magnitude of frequency response is only specified from 0 to pi, because in the negative frequency is exactly the same as the positive frequency. Magnitude h of e to the power j omega is equal to magnitude h of e to the negative j omega. It's an even function. Okay, so first we have two or three types of specification. The first one is the absolute specification. In absolute specification, if you go back over here, the magnitude of h e to the power j omega has to be limited between 1 plus delta p and 1 minus delta p as long as we are in the pass band. So, going back here, it simply says that magnitude h of e to the power j omega must be confined between 1 minus delta p and 1 plus delta p as long as we are in the pass band. So for omega between 0 and omega p. Where delta p, of course, is allowed ripple or allowed fluctuation or allowed deviation from 1 in the pass band, and for smaller values of delta p means a well-designed filter. A better filter would have smaller delta p. In the stop band, on the other hand, if you go back over here, in the stop band, you need your magnitude response to be always less than delta s. So we need magnitude h of e to the power j omega to be less than delta s as long as we are in the stop band, which is omega larger than or equal to omega s and less than pi. Of course, as you can see, here we are only talking about low-pass filters. This is a low-pass filter. It allows low frequencies around 0 to pass. It kills higher frequencies. And for the whole chapter, we'll be focusing on designing digital low-pass filters. Why is that? Because we have approaches to transform low-pass filters into high-pass filters or band-pass filters or band-stop filters. So we will learn how to design a low-pass filter, and we will learn the transformation that will transform a low-pass into a high-pass or any other type of filters. Okay, so the absolute specification, we need to have magnitude h of e to the power j omega within certain range in the pass band between 1 minus delta p and 1 plus delta p, and in the stop band less than delta s, which can be seen easily from this graph. In the pass band from 0 up to omega p, I want h of e to the power j omega to have the magnitude between 1 minus delta p and 1 plus delta p. And in the stop band, omega s larger than, for omega larger than omega s less than pi, I need to have h of e to the power j omega with magnitude less than delta s. This is called the absolute specification. The other type of specification is called the relative specification. In relative specification, we have normalized the magnitudes with respect to 1 plus delta p. So basically, we will divide all these values by 1 plus delta p. So if this is h of e to the power j omega magnitude, and this is 1, and here we have 1 plus delta p, and here we have 1 minus delta p, and here we have delta s. All these values will be normalized with respect to 1 plus delta p, which will make this one 1 plus delta p over 1 plus delta p, and here it will be 1 minus delta p over 1 plus delta p, and here it will be delta s over 1 plus delta p. So all values are normalized with respect to 1 plus delta p, and this basically will be the relative specification. So going back here, in relative specification, we want magnitude h of e to the power j omega to be between 1 minus delta p over 1 plus delta p and 1, as long as we are in the pass band. So here, if you take a closer look, 1 plus delta p over 1 plus delta p is 1. So you want, in the pass band, you want your h of e to the power j omega to be between these two levels, which are basically 1 and 1 minus delta p over 1 plus delta p. So in the pass band, you want your magnitude h of e to the power j omega to be between these two values over here. And in the stop band, you want magnitude h of e to the power j omega to be less than delta s over 1 plus delta p, which is basically you want it to be less than this value. You always want your h of e to the power j omega to be less than this value if you are in the stop band. So again, the relative specification, we have normalized all the levels with respect to 1 plus delta p. So now in the pass band, we want h e to the power j omega to be between 1 and 1 minus delta p over 1 plus delta p, and the magnitude of frequency response to be less than delta s over 1 plus delta p in the stop band. Moving on, usually the filter specification is usually defined in decibels. That's why the levels we have over here, which now would be 1 and 1 minus delta p over 1 plus delta p, and here we have delta s over 1 plus delta p, would be converted to decibel. So 20 log 1 would be 0 decibel, and 20 log this quantity we will call it minus AP, and 20 log this quantity we will call it minus AS. So in this case we will use the decibel values instead of the ratio, as we are going to see later on. So going back over here, so in relative specification we can also define what's called a pass band ripple and a stop band attenuation. A pass band ripple is 20 log 1 plus delta p over 1 minus delta p. So basically, if you take the logarithm of this quantity, it will be negative because the numerator is less than the denominator. It will be negative AP. So negative AP equals to 20 log this quantity. So flipping numerator and denominator will give you AP equals to 20 log 1 plus delta p over 1 minus delta p. So AP, which is called the pass band ripple, is 20 log to the base 10 1 plus delta p over 1 minus delta p, which makes AP a positive quantity. And AS is called the stop band attenuation, which is 20 log 1 plus delta p over delta s. So basically, if you go over here, taking the 20 log of delta s over 1 plus delta p would be a negative quantity because delta s is less than 1 plus delta p. So flipping the numerator and denominator, AS will be 20 log 1 plus delta p over delta s, as we can see in the definition over here. And of course, we can ignore delta p besides 1 because delta p is usually a very small number, so this is approximately 1 over delta s. So 20 log 1 over delta s is minus 20 log delta s. These two definitions are very, very important because usually the filter specification will be given in terms of AP and AS. And starting with AP and AS, you need to get delta P and delta S, which will be used in the design process. Note that the quantities AP and AS are positive quantities, and for a well-designed filter, AP should be approximately 0 or close to 0, and AS should be very large. How is that? Delta P ideally should be very, very small. If delta P is ideal, it would be 0, and now you get 20 log 1, which is 0. And here, ideally, delta P should be very small, and delta S also should be very small. So basically, we'll be getting 20 log 1 over a very small quantity, which is 20 log very large quantity, which is infinity. Or if you use this approximate definition, delta S, if delta S is very small, 20 log number, which is very small, will give you a negative infinity. With this negative will give you positive infinity. So AS should be very, very large, and AP should be approximately 0 or very close to 0 for a well-designed filter. So in relative specification, we need the magnitude of the frequency response in decibel to be larger than or equal to 0 decibel and larger than or equal to minus AP and less than 0 for the pass band, and in the stop band it should be less than minus AS. And again, let me talk about this minus sign because it causes confusion for some people. So going back over here, so if this is 0 dB and this level is AP decibels below 0, so this level is minus AP. And if this level is AS decibels below 0, so it's minus AS. So in the pass band, you want h of e to the power j omega in decibel to be between 0 dB and minus AP. And in the stop band, you want 20 log magnitude h e to the power j omega to be between or to be less than minus AS. Again, AP and AS are positive quantities. So here you are at level AP below 0, so it's minus AP. And here you're at a level AS below 0, so it's minus AS. So usually in the exam you will be given APAS, which is the pass band ripple and stop band attenuation, and you will be asked to design the filter accordingly. In this case, you will need to find delta P and delta S, and then you move on with your design, as we're going to see in the next lecture. Okay, so, and the last kind of specification is called the analog or continuous time filter specification. Why do we need to bother about the continuous time filter specification? Because as we have said before, in designing infinite impulse response filters, we start usually with the analog filter specification, and then we get to design an analog filter, and then we transform this analog filter into digital filter. And also in practical application, even for FIR filters, the specifications are given in hertz. So I will be giving you F pass, the edge of the pass band, the edge of the stop band, to be in hertz, and then you need to get omega P and omega S, the normalized frequency. So omega P and omega S, omega P is equal to 2 pi F pass over F sampling, Fs is F sampling, and omega S is equal to 2 pi F stop over F sampling. I know we have not studied sampling, so probably after I finish off this video lecture, I will have a supplemental video lecture to discuss sampling process and how it affects the spectrum and what is the relation between F capital and F sampling and F small and omega small and all this kind of notation. So for now, just keep in mind that omega P, which is this value we have seen in this figure, this omega P is equal to 2 pi F pass over F sampling, and this omega S is equal to 2 pi F stop over F sampling. Okay? So this is the first part of analog specification. The frequencies F pass and F stop are given in hertz. We need to transform them into the normalized frequency omega P and omega S. And in the supplemental video, hopefully, I'll be talking about this in more details. So, also in analog filter design, the quantities used to describe the ripples in the pass band and the stop band are quite different. They are called epsilon and A, and they are related to AP and AS as follows. AP, the pass band ripple, which is 20 log 1 plus delta P over 1 minus delta P, is equal to 20 log square root 1 plus epsilon squared. Epsilon squared, or epsilon, is the quantity used to describe the ripple allowed in the pass band, and it's related to AP in this way. So knowing AP, you can get delta P from this equation. Here, knowing AP, you can get delta P from this equation, and you can get epsilon from this equation. Or knowing epsilon, you can get AP, and then you can get delta P. And AS is 20 log A. So in analog filters, usually the specifications are given as frequencies in hertz, F pass and F stop, and as epsilon and A. Now we have an equation relating epsilon and A to AP and AS, and also we can find the normalized frequencies omega P and omega S in terms of F pass and F stop, which are given in hertz. Simply A is a ratio value corresponding to the decibel value AS. If AS is a stop band attenuation in decibel, A is a stop band attenuation in ratio, simply. And epsilon is another quantity that would specify that allowed deviation from 1 in the pass band. It's closely related to delta P. Okay, so now that we have talked about the filter specification, now we can talk about the filter approximation, which is basically if we have an ideal filter with impulse response h desired of n and desired frequency response h desired of e to the power j omega, we need to find a practical filter h of e to the power j omega which approximates h desired of e to the power j omega. So we start with an ideal desired frequency response h desired, but we look for a practical filter that can approximate this desired response. Any practical filter should be causal, stable, of finite order, and should be rational system of this form, which we have spent the past like 4 or 5 lectures talking about in Z transform, have been talking about this form. So the practical filter should be causal, the impulse response should start at 0 or after 0, the ROC of h of it should be going outward, it should be stable, so the unit circle must be included in the ROC, and these two combined together means that all pools should be inside the unit circle. It should be of finite order, which means it should have finite number of pools, and it should be a rational system function of this form. Now we can realize the importance of the previous chapter and importance of what we have learned in Z transform. So that is the objective of filter design, is to obtain 4 things: M, N, AN, and BN. Going back, so we need to find M and N and the coefficients BK and AK. So AK are the feedback coefficients. I need to find A1, A2, A3 up to AN. And the BK are the feed forward coefficient. I need to find B0, B1, B2 up to BM. N is the memory by which we remember the previous output, and M is the memory by which we remember the previous input. So how long is the memory that should be used to remember the previous input? How long is the memory needed to remember the previous output? What are the values of the coefficients AK and BK that should be multiplied by the delayed versions of the input and output in order to obtain this kind of transfer function? So the objective of a filter design is to obtain M, N, AN, and BN, or AK and BK, such that we get h of e to the power j that approximates the desired frequency response. Okay, so this will be it for this week's lecture. I will be having a supplemental video talking about the sampling process and the relation between normalized frequency and actual frequency.